Today we're going to do something slightly different, and related to the recent episodes in the core curriculum, I thought it would be useful to look back at some foundational work from 2015 published in Nature by the team at Google DeepMind. It's titled Human-Level Control Through Deep Reinforcement Learning, and it holds some of the most important lessons for anyone serious about building AI that can one day tackle the true complexity that we see in healthcare. What if a new junior doctor on their very first day could learn not just from the handful of patients they'll see that week, but from the collected experience of 1 million past cases, all reviewed in a single afternoon? What if they could learn to spot subtle patterns that even seasoned consultants might miss, not in one specific condition, but across dozens of different clinical challenges? It sounds like science fiction, but a decade ago a landmark paper gave us a glimpse into how such a powerful general learning system might work. It had nothing to do with medicine on the surface. It was about teaching a computer to play video games. The ambition of the paper was immense. The goal wasn't to build an AI that was brilliant at just one thing, like chess or Go. The goal was to create a single general learning algorithm that could learn to master a huge variety of tasks, with no special instruction for any of them. The AI was simply given the raw pixels on the screen and the game's score, and told to figure it out. The testbed was 49 classic Atari games, from Space Invaders to boxing, a diverse challenging set of problems. But to get there, they had to overcome a massive hurdle that had plagued the field for years. The technique they were using, called deep reinforcement learning, was incredibly powerful but notoriously unstable. Think of it as a brilliant but erratic student. It learns by trial and error, taking an action, seeing the result, and getting the reward or a penalty, as we've discussed in previous episodes. When you combine this with a deep neural network, things can go badly wrong. The learning process can start oscillating wildly, or worse, completely diverge and forget everything that it's learned. This happens for two main reasons. First, the data it learns from is highly correlated. One moment in a game is very similar to the next. It's like trying to learn about all of medicine but only seeing patients with a cough for a week. Second, as the AI learns and changes its strategy, the very data it sees changes too. It's like trying to hit a target that moves every time you adjust your aim. This is where the DeepMind team introduced their elegant solution, an agent they called a Deep Q network, or DQN. It had two key innovations that solved the problem of stability in deep reinforcement learning. First, they implemented experience replay. Instead of learning from its experiences in real time, the agent stored hundreds of thousands of past moves, the state, the action, and the reward, in a vast memory bank. To learn, it wouldn't use its most recent experience. Instead, it would draw on a random handful of memories from its bank. This simple trick broke the correlation in the data, creating a much more stable and robust learning signal. It's exactly like our junior doctor learning not from the patient in front of them, but from randomly reviewing 100 different patient cases from the last year. Second, they used two neural networks instead of one. A main network was constantly learning from the experience replay, but the target for its learning was generated by a second, separate network that was only updated periodically. This prevented the AI from chasing its own tail, creating a stable gold standard to aim for during training. The results were pretty spectacular. This single general DQN agent learned to play all 49 games. It outperformed all previous algorithms, and most famously achieved a level comparable to a professional human games tester across the board, even exceeding human performance in many of the games. In the game Breakout, for example, it spontaneously discovered the optimal strategy of tunneling through the side wall to let the ball bounce around the top, an emergent, non-obvious piece of long-term planning. So what are the lessons for health AI? First, the paper was a monumental step towards generalizability. It showed a path for creating a single model that could learn diverse tasks from raw, high-dimensional data like pixels. For medicine, this is the dream, an AI that learns from raw CT scans, ECG waveforms, and ICU sensor data without needing a bespoke, handcrafted solution for every single problem. Second, the principle of experience replay is very relevant. Clinical AI systems must be robust. By learning from a massive randomized library of historical patient journeys, we can build models that are less biased by recent trends in the specific patient populations of a single hospital. But the paper also teaches us that the current frontier, the DQN, struggled on games that required very long-term planning with infrequent rewards, like the infamous Montezuma's Revenge game. And this is precisely the biggest challenge that we face in healthcare. The reward signal for managing a patient with diabetes or heart failure often isn't a quick score on a screen. It's a quality of life outcome measured over months or years. Solving this sparse reward problem is the critical next step. The DQN paper wasn't really about video games. It was a proof of concept that solved the core problem of stability in deep reinforcement learning. It gave us a blueprint for creating more general, more robust learning agents, and in doing so laid the groundwork for many of the AI advances that we see today. It's a vital reminder that our goal isn't just to build algorithms that are clever, but ones that are stable, general, and ultimately trustworthy.